This session is on the theorem itself, the first isomorphism theorem. So I'll give a little bit of background and state what the theorem is, particularly in visual form. Makes it easier to understand. I mean, you can just see this kind of one-to-one mapping, which is what the first isomorphism theorem is all about. And then a little bit of background for the proof, and finally the proof itself. And for the next session, I think four examples of the use of this theorem. Yeah, 4. And then there are only 5 exercises, questions at the end of the chapter. And in this case, because it's the last lecture of the whole book, the whole course, it will be the last exercises of the book. And there are only 5 of them. And most of them are sort of theory type questions, so I may do quite a few of them. Alright, so this session is about the theorem itself. So what is it? Well, your mapping function f has to be homomorphic, but it also needs to be surjective. Remember, surjective means that every member of your codomain, your target set, gets mapped to. Right? There are no loners. There are no elements in your target set that are not mapped to. Right? So every element in the codomain, target set, same thing, are mapped to. Okay. So imagine you have a function that is surjective. Sur, reminder, sur is just a French word for on. So an onto mapping, if you like. Every element gets mapped to. Okay. So assuming a surjective function that maps a group G to a group H, right? Then if it's homomorphic, if that function is homomorphic, then you can find the kernel, right? And once you've got the kernel, you can create quotient groups of this group G. You know that, right? So find the kernel. Remember, kernel is the subset of G, all of whose elements map to the unit of your group H, your target group. Okay? So find the kernel, and then find the quotient group. So G slash K. Oh, here. G slash K, where have I written it specifically? Here. Okay. So find your quotient group once you know the kernel. You can find the kernel from your F. Right. And once you've got the kernel, you find the quotient group. And once you know what the quotient group is, you'll have then a set, or group actually, of cosets. That's what a quotient group is. And each of these cosets, now I've drawn it here in like dashed lines. So this little grey, blue block here is a coset, right? And each member of that coset maps to the same element in this target set, and this target set is just called the image. It's the image of F. Ricky, you go way back to, I think, is it chapter 2, I think, on sets. What is an image? Bit of revision. An image, well, if you have 2 sets, so S and T, let's say, and here's an element S, and it maps to an element in T. This element in T is called the image of this element. Right? well, I'll just leave it at that, right? This is the image of that one, because this this element is mapped, I'll call it F if you like. It's a different F from here, it's confusing. What do I call it? P, mapping P. So P maps this element into this one. And this resulting element is called the image of this one. Okay, bit of revision. Alright, so all the different elements that get mapped to from these cosets, so you have a set of images, if you like. So an image set, which is usually just called the domain. So you could call this just the domain, if you go way back to lecture 2 on sets. Right? So this group here is called the image of F, and it's usually shortened to just im of F, the image of F. Okay, and the first isomorphism theorem simply says that there's an isomorphic mapping between these cosets and the elements in im of F, the image of F. Right? You can just sort of see it visually. Okay. Now, to make it sound more plausible, each of these sort of bars here, they represent, you know, this sort of region here, this stripe. In fact, a fibre. If you go back to what, two lectures back, several lectures back. So each of these subsets here, which is a coset, each coset maps isomorphically to one element in the image of F, this target group. Right? One coset, one member, and this member here, what is it? It's the image of every element in the coset. Each element in this coset maps to just one element here, right? So if I had A and B, members A and B in this coset there, f of A, because we're mapping with the function f, right? F of A would equal f of B. So those two members, A and B, are in this coset, and they both map to the same point, if you like, the same element in your image of F, in your target group, target set, right? Okay, so imagine this coset, if it contains the unit of the group G, then that coset is the kernel. Okay? It's the kernel. Because remember, every element in this coset maps to the same element in the image of F, in this target set. And what is that? What is that image? Well, it's the unit of H. Remember, we had a theorem that the unit of G, the unit of your starting group, maps to the unit of your target group. Right? So E of G maps to E of H. That was one of our theorems. And so all the elements here that map also to E of H, by definition, those elements, the set of those elements, or the subset, subgroup actually, normal subgroup even, map to the unit of the image. Okay. Now take other cosets. So take this one and imagine. Well, there's an element in, say, element X. I don't know if you can see it, little X here. So f of X will map to, let's say, S. This element S in the target group. Okay. So all the other elements in this coset also map to S. Right? Now take another coset, a different coset, and it contains the member Y, little y here. So all the elements in this coset will map to, let's say, a different element from S, but element T in your target group H. Right? Now F is a homomorphism, right? So we've got this coset xk. So remember, if X belongs to a coset, that coset is xk. That was one of our theorems. And so if y belongs to this coset is yk. Alright? Now, because f is a homomorphism, then here's your homomorphic property, what I've been calling f of mn. But now, well, getting used to it in the homomorphic context, we could call this now the homomorphic property. Right? So f of xy equals fx fy. Right? That's the condition for homomorphism. That's the test. Okay. Now because f is homomorphic, f of xy equals fx fy. And what's fx? Well, f of here maps to s, right? So fx is just s, and f of y, well, f of this maps this point y to t. Okay, so fx fy is st. So fxy maps to st. Right? So this point here in this coset xy, it will map to st. Okay, so and that's a consequence. That's a consequence, you know, that this xy maps to st, which is the product of these. And these, if the product of two cosets, now remember we're talking about a quotient group, right? And what are the elements of a quotient group? Well, they're cosets. And a quotient group is still a group, so that means a binary operation on that group must be defined. And so you must have some kind of binary operation on the members of your quotient group, and that's what I've been calling subset multiplication, where the binary operator used in that subset multiplication is taken from your original group G. That's the same binary operator as G. Okay, so when you multiply two cosets, you get this. So you get this relation, which you've seen quite a few times already. I'm talking about multiplication of, well, binary operation on two cosets. Right? So visually, you can just sort of see that there's an isomorphism between the cosets. And the cosets map in the same kind of way that these map. Like the binary operation on st gives you st. Binary operation on these cosets gives you another coset which maps to this. Right? It's looking very much like an isomorphism. So that this is a kind of visual motivation. A visual makes it plausible that. This theorem. Now, the actual detail, the theorem, the rigorous proof, will be on this side, but this side is more to it's more a motivator. So you can see that it seems plausible. Right? I mean, just visually, it looks okay. And with the binary operation in this group, x times y. So this maps to st, which is the product of st. So. It looks isomorphic. All right. So the actual statement of the theorem. So it's now theorem 64, which is called in the textbook the first.